Cool. So I guess for today's journal club, we are going to kind of read a paper together, the Generative Image Dynamics, which is the 2024 CVPR's best paper. Yeah. And for today's agenda, I'm going to share, my own understanding about this paper, what it's doing and what interested me. And feel free to, raise any questions or comments. But I might keep, the question and the discussion part, at the end. I might spend around 40 minutes on the paper. Yeah. Cool. So I might continue. Yeah. So this paper is called the Generative Image Dynamics. Before we jump into the paper itself, I might show you some demo the authors group kind of they created. Sorry, why? Okay. Yeah. Oh, yeah. And also, I have a quick disclaimer. I wouldn't claim myself kind of expert in this area. So I would say the brilliance of this work belongs entirely to the original authors, and any misinterpretations are solely my own. Yeah, because I might have some kind of knowledge gap. Yeah. Cool. Yeah. So first of all, let's look at some demo they created. Yeah. So everyone can see, right? Okay. Let me zoom in a little bit. Yeah, this is coming from, this paper comes from the Google research group. So what they do is their resulting model, it can kind of convert the input still picture to some seamlessly looping video. So you would see the rows is always kind of swaying a little bit. And also that we can have some interaction with this picture. For example, you can see the arrow, which showed a second. So that is someone has pulled the rows. Then it will kind of swaying towards that direction, which is very realistic motions. Yeah. And they also have other examples like the graves, the wind, the candles, flickering candles, the flowers. These are kind of more dynamic things, which converting kind of the still pictures to make it seem to be more realistic to human eye. Okay. So I might skip, the abstraction, these stuff. Just want to understand, what's the paper's application, immediate application they can do. Yeah. So something like this one, we can try it ourselves. Like for example, the rows, I can drag it here and it will, if I drag very small, then you can see the motion is got smaller. Yeah, I can drag to different kind of directions. Yeah, and it always makes me feel okay, this motion is very kind of aligns with our life a lot. Oh, and also you might notice what makes it seems to be kind of very kind of realistic is kind of the details are really good. For example, the pedals, these details are not lost when it has the motion. Yeah. So
is this entire rows generated?
Yeah, the following pictures are generated. The first still picture is the input. And of course, your drag, your action is also input.
When you drag the rows in the background is also moving. You can try this.
Really?
The rows in the background. If you try the rows in front, the rows in the background is also moving.
Oh yeah, right. When I kind of when the arrow kind of cross the roses in the background. Yeah, you can notice the background is also kind of swaying a little bit. Well, good catch. Yeah. Yeah. So of course, they present more cases yeah, for this one it might I feel like this one it has a little bit kind of a resolution or kind of a weird thing, but in general it looks good. Yeah. So yeah, so this is kind of what you can interact with the pictures. Yeah. And lastly, in this one, they're showing, okay, they can actually kind of control the motions. They can kind of magnify it or kind of minify it, make it larger and smaller, controlling the motion. Yeah. And also kind of make it slower or faster. Yeah. Yeah, so that's kind of like the applications of this paper, the author think. Yeah. Yeah, after we see this demo, then we can, like jump into like how they did that, kind of the magic behind it. Yeah. Yeah. So first of all, I would say like behind it, it's a model. And actually, sorry, I felt like this is not the, uh, let me see, I might, okay. Sorry, there was kind of some miss. Okay, I guess. Oh, okay. I recall. Okay, sorry. Yeah. So I guess like first of all, I would talk about okay the whole kind of like targets of the model behind it. What you can see like the objective, like have you noticed like any kind of characteristics what we observed about the motions they want to capture? Yeah. So here I would say like the motivation behind it to capture that kind of specific motion is human sensitivity to motion can cause imagery without motion to seem uncanny or unreal. Because we know like the real thing usually it seems to be still, but actually something always move like very kind of like gently. Yeah. So the authors kind of group, like they believe the subtle oscillations is crucial in the visual content synthesis to make something kind of look more real. Yeah. So what they want to do is to train a model to learn this realistic same motion. Yeah. So those kind of small changes in kind of seemingly kind of still things. Yeah, and how to do that, they think they want to kind of train a model to learn the distribution of natural oscillations. So for example, like these are real kind of videos. So you can see like, for example, like you can observe this candle. It would flicker and kind of become smaller and kind of become kind of a larger kind of like a light. Yeah. And for the second one, it's the tree swaying. So you can see like it goes left and left and right. Of course, like up and down. There are kind of two directions. Yeah. So some characteristic we can conclude here is, sorry, maybe it's the video kind of, yeah. Some characteristic here you might see is like, there seems to be some pattern, right? Like it only kind of like change in that range. For example, like the leaves, it wouldn't kind of like directly go from the right side of the picture, jump to the left side. It's not realistic. It can only kind of like, there seems to be a distribution of these kind of small motions. Yeah. So that's the author wants to kind of capture. Yeah. And then a quick overview about how they do this is like their starting point is an input picture, which is still on the left side. And their whole architecture include like two big parts. One is a motion prediction module, which is actually the gray arrow here. This module would output something called a spectral volume, which is also, you can imagine it as an image space model basis. I might kind of dive a little bit deeper into like what is that and kind of like why the author choose to kind of represent it in that way. In some details, some hints you might get it from the middle part, the spectrum volume. You can notice like there are kind of 0.2 hertz, 0.4 hertz, 3.0 hertz. These are all frequencies. So that's some hint. And also in the downside, you can see like in the bottom, there is the X coefficients and the Y coefficients. So that kind of give you some hints like, okay, the author kind of predicted this spectral volume kind of in two directions, which is the two directions in the 2D space, right? The X axis and the Y axis. Yeah, so that's the first module about the prediction. And the second module is about the rendering module. Yeah, it will convert the volume into a picture, not a picture, I mean like the trajectory of motion, which would convert into a video, yeah. So that's the overall view, like the whole architecture. Then we can look into kind of like the components. So we will talk about the motion prediction module first. So just kind of like take a quick look at this picture. So this on the left side is the encoder, on the right side is the decoder, and the S, F0 stuff, this all is S. They're the spectral volume, the whole output. So that's kind of this might be kind of like too many things in one picture. So I'm going to break it down into several kind of steps.
Question?
Sure.
What does this image mean? The different color.
Yeah. We will talk about that later. Cool. Yeah. So on the a hint is like the left side there is the spectral volume, but we will dive into that a little bit more. Yeah. So yeah, exactly. Like so I put like we are going to look at the output first, and then we kind of look at the technical detail, like how they train this and what's the architecture. Yeah. Okay. So yeah, sorry. So for that part, what they are doing is like they want to kind of the output is going to be kind of a motion representation. Yeah. So before we kind of go to the spectrum volume, first of all, we kind of need to think like, okay, how we capture motion. Yeah. Here, the author kind of borrowed here, the author borrowed the motion texture from other kind of like papers and other works. High level, intuitively, like the motion texture is a sequence of time varying to the displacement maps. For example, like here, the T is a time step, so it includes the time. And for FT, actually that represents like for each pixel, and on the 2D dimension, the x-axis and the y-axis, how much it would move. Yeah, so you can imagine like it is tracking a point and on the picture, and at the when the t is 1, for example, it's in the center, and when t kind of keep increase, we are dragging it to the right, then you can imagine like this point would move from like the left side to right side gently, like a step by step, until kind of the final T, the big T, it will reach, you know, like where you want it to be. Yeah. So it is, yeah.
Can we understand it as like the delta X and delta Y?
Yeah, that's one kind of that's something you can kind of picture in it. Yeah. So that means like for each pixel, it can track like the trajectory it will travel in the future time. Yeah. And so something else it will mention is the forward mapping. So here is, you know, like how we convert from the original location to the future location. For example, like I here is image, because like, you know, like a video is actually kind of a bunch of image, kind of like a kind of we sequence together. Yeah. So I0, that is the first image. Yeah, the original one. And IT is the image we would see at a future time T. Yeah. So you can see like, and P here, P is the pixel. Yeah. So you see like the original picture, this pixel, kind of like the difference between the original one and the future one is the FT. It would tell you like how it moved. But of course, like in this formula, you can see like P is plussing the FT equals the original one. So it's kind of like the other direction. So it is kind of like tell you the delta, but in the other direction. Yeah. And after that, so you can see like for each P, that's the trajectory. And then it is something called the fast Fourier transform. So it will convert the T kind of like, it will kind of throw out the T. You don't have to keep that. It will transform it to spectrum volume. So what's the difference between the spectral volume and the kind of motion trajectory is like the T is gone, but actually something is added to it, the frequency. Yeah, so that's the prediction module output, the spectral volume. So here, one key message you might want to kind of memorize is like, okay, there is a motion kind of trajectory map. It can tell you like everything, where it moved, where it ends at the future time. And also this motion texture can be encoded into the spectral volume. These two are kind of, you can transform one to the other or transform it back. Yeah, here's kind of a little bit jump, like, so I'm going to tell you like where this T is going, like why it's gone. Yeah. So here, it will talk about something called like a Fourier domain versus time domain. Yeah. Here we can see a quick example. Let's see. Okay. It's yeah, I hope it can kind of like show the high level idea about this, because personally I find it might take some time to understand all the kind of like information. But here maybe just grab a kind of like a high level idea in this quick like introduction. Feel free to check all these links or the papers in kind of like all these kind of like blog posts later. Yeah. Here, one message I just want to tell you is like for time domain, that means like the x-axis is time. So it's like a function of time. You need to kind of input the time value, and then it will tell you, okay, where the location would be, something like that. Yeah, so that means your input is time. And for Fourier domain, it also called a frequency domain. So that means like the x-axis is no longer time. It will be changed to frequency. So you can throw the time away. How you throw that away in this picture, it uses something called winding frequency. Yeah, the winding frequency just tells you, okay, how many circles per second. So you don't have to tell it like the second anymore. You just need to tell it how many circles, because the time kind of idea is already absorbed in the winding frequency. Yeah, does that make sense? Yeah, if it doesn't like kind of give you the all details, yeah, just take my words for it, take a leap of faith so far. Yeah. So this means like the top picture, we're still in the time domain. After the transformation, we will go into the frequency domain, which is also Fourier domain. So the x-axis is frequency, and it's described kind of like, okay, how kind of like, what's the wave look like? Yeah.
What does the energy mean here?
Oh, actually energy here, in our case, we might not kind of like use that concept exactly, directly. Yeah, energy here is kind of more a concept in the Fourier transform. So it is saying like, it's kind of like
amplitude.
Yeah, amplitude. It's kind of like a concept in the wave, like how strong this is, like how strong this wave in this combination of frequency. It will go deep into kind of like the Fourier transform, which is decomposing kind of a wave into different phases. So you can imagine like all the waves, they're a combination of kind of like a group of basic waves. Yeah. So it will tell you like, okay, if we are coming back like from the right side this way, if we want to understand the component in this way, yeah, then this transformation can tell you, yeah. So yeah, there might be some more concepts. Oh, sorry.
Sure. So if we make the signal graph dense, very dense, how does this following two graph look like?
It will still, like depends on kind of the winding frequency. Yeah, because like
So the frequency will like smoother or like will be grow bigger or
no. Yeah, so it's a little bit kind of like a kind of a divergent from our key points today. Yeah, I feel like we can follow up like after this. Yeah, because the question you have is more about like the Fourier transform, these kind of concepts behind it. Yeah. But I would like to, like give all the people the kind of the idea of this paper first. We can talk later. Yeah. I know that's a fascinating kind of concepts. Yesterday no, last week I also kind of like look into that, try to get some more understanding. There is a question from the Zoom. Is there a WeChat group? Yes, there is. Okay, very great. Thank you so much. Yeah, I was wondering like if he do not have the WeChat group, like how did find this? Okay,
The email list maybe.
probably yeah.
I got
yeah. So here we talk about the Fourier domain and the time domain. So that it kind of give a very quick like concept about why about like how we kind of convert from this to this. Yeah. And continuing yeah. Okay. Yeah, so of course, like feel free to kind of dive deeper into, like this link. Personally, I find this material kind of has from, for instance, has more context about the frequency, all these stuff. Yeah. So the basic idea here is like when we modeling these motions, we actually interpreting it as, like a combination of waves. And all these waves have its frequency. So it might give you some hint or kind of like remind you some kind of pattern we observed from our target. So for example, like the candle, the swaying, something they share in common is like they are quasi-periodic. So that is kind of what a wave is, like the frequency, right? They're always periodic.
What is quasi-periodic?
That means like they're close to periodic, like they're not exactly like always repeating themselves, but kind of close. Yeah. So the periodic kind of characteristic kind of makes the authors think, okay, why don't we kind of use a frequency to represent these motions? Oh, sorry. Okay. Yeah. Yeah, and also like a continuing, what other benefits we might have with the Fourier domain? First of all, like the author in their study, and also they looked at some kind of previous work, they find out like the motions they want to capture can be represented pretty good with the all these frequency. And the frequency, you don't need like a very complex basis. You don't need like 100 different bases. In this case, they find out like only 16 frequencies are needed. So it's 16 bases you're looking at. That's kind of like in terms of scalability, that's very good because here, this K is the frequency band you would need. In this case, it's 16. And when we kind of creating the videos, like sometimes we create very quick videos, but sometimes we can create like a couple minutes, even 10 minutes video, then that makes the T very large. Yeah, so in terms of scalability, in this way, we can make the information more condensed. We can kind of create infinite video loop with very kind of like a dense information instead of like a huge kind of output. And the second thing about this frequency concept is like it has a temporal consistency because you never see like some wave, it will kind of sudden change, jump around like in terms of the value. Yeah. So the consistency is almost guaranteed. Yeah. So this is about, like the output side, why the author choose the spectrum volume to be the kind of motion representation, what they call, yeah. And then I would dive into how they kind of let their model output a good motion representation. Yeah. So here, this is about the model they use to kind of capture the pattern, which is a latent diffusion model on the left side. It has some encoder and some decoder, and in between there is a denoising kind of like a chunk. So let's break it down to two processes for this diffusion model. On the left side, this is the diffusion part, and on the right side, this is the blue part is the denoise part. Yeah. So for the diffusion part, here the most kind of this description and statement are about the training. So in training, the noise itself is our target. So we kind of generate the noise and then we predict the noise so that we can learn, okay, how to denoise the stuff. And in the inference, it's totally different. If we create, our target, then it's not inference, yeah. So here in the inference, we just sample a Gaussian noise. So then we look at, the diffusion process. We focus on the training part. The first step is we need to initialize encoding the noisy latent zero. This one is coming from the encoder piece of the variational autoencoder. And here the S is a spectral volume of one the first frame of this video, yeah. So it's have the starting point. And then this is our first part of the noise. And then in the forward diffusion process, we can just capture this concept. In this paper, the author didn't give the details about how the noise is added, but overall the concepts should be very similar to other diffusion model. In this process, we would continuing add more noise to the noisy latent to make it noisier and noisier. So you can see like N is the step, assuming like we kind of like break down the noise addition into N step, yeah, big N step. And in any small N step, you can imagine it as the noise latents from the previous step and plus some more noise. Here, just borrowing from other kind of like a diffusion paper, the idea, usually like according to the schedule, there is a kind of a proportion of Gaussian noise is added to the noisy latent. And here the beta n is beta n. According to the paper, there is some predefined variance schedule. They didn't tell us like what the schedule is, but it's okay. So we just know like, okay, for the schedule, it tells, okay, for each step, how much noise is going to be added. Yeah, that's the idea. So you can imagine, like a process go like the noise is keep kind of like build up. Yeah, until like finally you might see a very noisy picture, like how much noise it is. Yeah.
What is Z? Sorry.
Z is a noisy latent. So that's kind of, yeah, let's see this picture. All these seems to be kind of very similar, but actually it is kind of like yeah, I feel like a better visualization might be like for the first one, the initial one, it might have kind of like a less noise, like a kind of more picturey stuff. In the later one, it should look more similar to a Gaussian noise because it's adding more kind of Gaussian noise to it. Yeah, so it's actually measuring like how much noise there is when we want to kind of like convert, kind of like mask the picture. Yeah, we kind of like when you can imagine like if we added the noise latent to the original picture, then the picture would be kind of like a blurry and kind of like not that clear. Yeah. Just notice kind of there might be some message in the Zoom. Okay. Oh yeah, great. And Haoxing just shared a link in the Zoom chat about the diffusion model schedulers. Yeah, feel free to check out the link. Yeah, if you're interested in the scheduler part. Yeah. Okay. So continuing, we know, okay, the diffusion process, it's kind of like creating more and more noise on top of the original input. And here, I would give you the training objective first, why we need this noise. Actually, this noise is treated as kind of the, how to say, like a target. Yeah, because the model needs to learn how to kind of like the denoising part need to learn how to kind of remove those noise. like it needs to kind of recover the original clean picture. Yeah. So here, and one called is like this training objective. It's for the whole latent diffusion model. It's not just for the diffusion process, since diffusion process is mostly that's okay. Mostly about kind of creating the noise. Yeah. And here, one thing you might notice is like C. The C is the embedding of any conditional signal. So that means like we can give this latent model something to start with. In this case, we want to give it the, in the training process, we give it kind of the starting picture. Yeah. Cool. So that's about adding the noise. We create the noise, and then about how to remove the noise. Yeah. So there is on the left side, you can see, like on the left side, which is not in the red dotted kind of blocks. This is a whole structure, and the red dotted blocks actually is used to explain, like one component for the iterative denoising. So it's kind of zooming in, like focusing on small component. So the overall kind of architecture is on the left side. On the right side, there are more details. Yeah. So for the denoising part, the author also did some kind of like innovation in there. For this denoising, the input is not only like latent, the noise latent, and also the original picture. It also have the time step embedding, because like for different steps, the noise is different. And also it has the frequency embedding because it has, like if you recall that from our motion representation part, all these kind of like motions has different frequencies. Yeah. So in this case, the author wants to, like after the denoising, the output is actually a picture in the future. So it wanted to capture the frequency, the motion, which is, yeah. And in this case, like the author called this module frequency coordinated denoising. I will kind of like have a quick explanation about what is frequency coordinated, why it is called this way. Yeah. So this is the general picture. You can see like the denoising, kind of like a module look like. And then for like this big denoising module, the component it has, like the most important components is a spatial layer and a frequency attention layer. Yeah. Here you might notice like for the training process, what the author did is like they train the spatial layer first, and then they freeze it. Yeah. And the second layer on top of it, they add the frequency attention layer to it, interleaved with the spatial layer. So you can see like it's the denoising component would be spatial layer, attention layer, spatial layer, attention layer, something like that. Yeah. So you can imagine it continues. And here, actually, you would notice there is a kind of a skip connection. You kind of add the frequency attention output to the spatial layer output. So they can be combined together. Yeah. About why this would give, the called like a frequency coordinated denoising. So the high level idea is the attention layer, by doing this, the attention layer would learn to coordinate the denoising process across different frequency band of the spectrum volume. And why is that is because for the 2D spatial layers, you can notice like its dimension. Here, the B is the batch size, K is a number of frequency band. They're kind of like they're already kind of like together. One sample kind of like and not one sample. For the kind of training process, it will treat it as BK samples. So that means in this layer, it will process each frequency band independently. Kind of they wouldn't kind of be combined together or kind of like the model wouldn't consider the correlation. Yeah. So they treat the batch as a BK samples instead of B samples. Yeah, so that's why the frequencies kind of are independent with each other in this perspective. And then it's frozen. After frozen, for the attention layer, you can notice like there is a reshape. In this time, the B and the K are kind of separated. And then they perform the attention across the frequency dimension. So that means like in this way, the attention layer is aware, okay, all these K stuff are belong to one sample. So it can learn, like the relationship between it. So it can coordinate between the frequency bands. So that's why the author, build up this this layer and kind of like thinks it can fulfill the target of coordinating frequencies. Yeah. And about why the author care about the frequency coordinated that much, does it really have a meaning? Is like down below, I listed 2 other alternative approaches people might have commonly, kind of like in common practice. The first one is like when you're when you're denoising, one common approach is like, okay, you can just output a 4K channel in one model. So that means like everything is predicted together. And this usually is observed like they might have over smooth and inaccurate output. Yeah. And so if you don't want it to be over smooth, some other thing you can do is like you can independently predict the frequency slice. That means you would kind of doing like the purple blocks doing, like you're treating each frequency band like independently. And what might happen is like in your prediction, all these frequencies are not correlated. And what this can lead into is like the uncorrelation between them can lead into unrealistic motion, because you might see things kind of like suddenly jump very fast or something like that. Yeah. So that means like the consistency would be kind of probably can be broke. Yeah. So that's why in the denoising, the author wants kind of frequency coordinated layer. Yeah. So this is kind of like in total gives you like how the noise part and the denoising part got kind of work together, and then they output the spectrum volume, which tells the motion trajectory for each pixel. Yeah. So that's the kind of prediction module. Yeah. So you can think, recall a little bit is like, okay, this one, it intake like the original picture, or in the training, it's the first frame of your clip. And then it output the kind of motion trajectory, like for each pixel in this picture. So that means actually you can convert all these motion to kind of a future group of images. That's a video then. So that's the prediction part. However, of course, like in the prediction result, that's still a representation. It's some kind of information about the kind of motion. It's not a picture. So we need the rendering module later to kind of like convert all these motions back to images. Yeah, that's the rendering module. Yeah. Maybe we can have a very quick look at this one. It's like I0, that's the first image you will see, and then it will be converting to some features, and it combined with something we learned before, FT. If you recall that FT is kind of directly related to our prediction result, which is spectral volume. There is a transformation between them, and there is a new information W. I will talk about W later. Yeah, it's a quick conversation. Yeah, and after that, you would get some kind of like a features, we call it like a webbed features. And then all these features, you can kind of feed them into the synthesis network, which kind of like a decoder, just like the intake some kind of numbers and convert it into the RGB, all these kind of like pictures. Yeah. So that's a high level idea. So here, this is how the authors did. What they did is like the feature pyramid softmax splatting strategy. It's very lengthy. So let's break it down a little bit. So feature pyramid, that means like for the information that generate, they would have multiple scales. For here, the multiple scales, that means like there are multiple resolutions. You can imagine like some picture are very, very small. When you zoom in, it kind of become very blurry. So that's one scale. Or some picture are very huge and everything is very, very clear. That's high resolution, right? So in this case, all these feature pyramid, like all the information you generate, they would have different resolutions. Yeah. And the softmax. Softmax is kind of a splatting they did when they kind of like converting one pixel to the final pixel. Yeah. Here I might kind of like talk about, like at the right side, the dotted box a little bit, why the softmax is needed. Although we, like we already assuming like we already have the information about the one pixel, like we track, okay, at time t, it should move to, for example, like some area. So this is kind of a regular splatting people did, like a wrapping kind of the pixel around. But can you imagine like what might be wrong in this process? Yeah, am I cool. I can reveal like okay, so when you are moving all these things, like you can imagine like in a room, like people are running and we're telling people, okay, so okay, this lady, you should move to that seat, and this lady, you need to move to that corner. So at the end, there is something happening. It's like probably all these seats, some seats might be empty. Yeah. Why? Yeah, because like probably no pixel is kind of like arranged to that location, right? So there will be holes in your picture. You can see like there's nothing. And another thing might happen is like probably our model can make it something wrong, like we can put like two persons in one seat. So that's overlapping. Yeah. And when it happened, like what we should do, like should we override or do something else? So that's why the softmax is needed. It kind of coordinate everything. Yeah. So what it did is like they splat the pixel value across its neighbor. Yeah. The neighbor of the target location. So, and all these contributions is kind of like a softmax. So it's like aggregating everything together, weighted by the softmax function. So it can solve, like there wouldn't be a hole, there wouldn't be kind of weird overlaps. Yeah.
So it is a softmax, and it's not a trainable module.
Let me think. It's a trainable part. So the feature extractor, I will talk about the feature extractor first. So this part is trainable because it's actually a network. Converting kind of the original picture is kind of like a encoding kind of like a process, like converting the original, the first frame into some kind of embedding or these numbers in different scales, of course. Yeah. And also there's another kind of like a trainable part after the softmax splatting. The splatting itself is kind of, in my mind, it should be just one algorithm. Yeah, probably no trainable parameters. Let me check the Zoom. Someone mentioned there is echo, really? Yeah, let me know if that resists. Okay, it's good. Okay, cool. Okay, let's move on. So yeah, so we kind of explained like, sorry, let's go back. We explain, like the soft splatting strategy, this stuff, then we kind of combine everything together to look at the whole picture. So if you recall, the SP, P is a pixel, S is the prediction result, the spectrum volume from our prediction module. Yeah. And then the FFT -1, that is, like, do you feel like that is familiar to you? Something we mentioned earlier? Yeah, exactly. Yeah, previously we mentioned, like the spectral the transformation between the spectrum volume to the motion texture is the faster Fourier transform. So it is inversible. So that means we can use our prediction without the representation and to get the motion trajectory. So it tells the trajectory. And then this trajectory, we can actually use it to calculate some weights. For the weights, yeah, I didn't find kind of a lot of details in that. We can just just call it like a weight. I think intuitively, what it means is like it can identify something with larger move in the front and something with smaller move, smaller motion. It's in the background. So you can see like the picture. Yeah, like the kind of like stronger color, they have kind of higher kind of like motion, and in the background, I think this might be the rose one. Yeah, the background is kind of like it has smaller motion, these stuff. Yeah, so it kind of like tell the model, okay, this is the main object, our leading role, and these are kind of our background scene. Yeah. So that explains, like the rose one, when I drag it very kind of like strongly, the rose in the front, it's kind of like sway kind of larger than this rose sway in the background. Yeah. So that's the two inputs. And on the left side, you can see there is a feature extractor we just mentioned with multiple scales. So with kind of these scales, it can, like have a lot of benefits, kind of about, like kind of like some, for computational wise, it's kind of more efficient. And also like for the information wise, it can capture kind of the big picture and also the remain kind of containing the details. And this kind of mimic what happened in our physical world. Yeah, so usually like something we can observe it kind of from a kind of bird eye, and also we can observe it kind of like a very detailed way. Yeah. And all these stuff, we kind of combine everything together. And then the output is also multiple scales. It's a webbed feature at multiple scales. And this would be feed into the right side, the synthesis network. Yeah, for the synthesis network, I didn't find a lot of details on that, but the main idea is it can convert everything back to the picture, the RGB channels, and you can see kind of the, so what the image would become at time t. Yeah. And about the training process, all the feature extractor, synthetic networks, everything is trained all together. Yeah, and how you got the training data is like you have a lot of videos and you randomly sample the clips from these videos. So you would have your initial frames and also the target frames. The target frames would be your, like a ground truth. And here they use a training loss, which is called a VGG perceptual loss. You can click on this. I put the paper link there. It's a loss function, I think, brought about from Li Feifei's team. Yeah, and a quick idea is like it's a combination of perceptual loss, which kind of is looking at the big ground truth, the big picture. Like overall, does this, like video make sense? And another part it has is a per pixel loss. So you would examine, okay, whether each pixel makes sense. So it means like in high level idea, it's capture big picture and small detail. Yeah.
What is rendering?
Rendering, I think rendering is kind of like I didn't really look at it, but my kind of like intuitive understanding is it converts all the numbers, the embeddings into a picture, like the RGB channel, like which channel should be like the number of it. So you would have for each pixel, you should have 3 channels, right? Like all these numbers. Then it will kind of like convert the numbers to these channel numbers so that you can kind of like make it like a picture.
Right.
Yeah. So
my understanding is the previous model trained to get the color picture, the frequency domain.
Yeah.
And now we need to use this frequency domain to convert the RGB image to its motion image. Is that what like really?
The rendering actually In my understanding, actually, the rendering, yeah, reconstruction from the embedding part.
From latency domain to the spatial domain, that's the reconstructed the pixels in the spatial domain.
Yeah, that's my understanding. I guess like a little bit different from what you mentioned is, I guess, is its starting point is already in the latent representation instead of the original picture. The original picture is the input of the prediction part. But of course, in this case, the feature extractor also used the original picture. The original picture is used multiple times. Yeah.
Okay. Okay.
I mean, I feel like it just in this case, I mean, like for the author, the rendering module did this, like combining the kind of feature extracted from the original picture and the prediction representation. Yeah, in the frequency domain.
And combine together and then using synthesis network back to the spatial domain.
Yes, in this paper, I mean, like,
right.
yeah.
Yeah, I think so.
Yeah, I think your idea actually is similar.
Yeah, just
cool. Not only the, but also the latency domain of the feature from the image.
Okay, so but although it's drawn it as RGB domain, image domain. Actually,
This is the link.
Okay, so it has
and this from the frequency. This from this latent. So we combine together.
Cool. Yeah. Oh, yeah. So I guess like we might continue since we only got the room like until 12:30. Actually, we are over time. Yeah. So I think that's all the kind of like a rendering and the prediction module and all the applications. So I think it covers most of the paper. Some other kind of interesting tricks the author did. You can look at the paper about, like the frequency normalization. That's personally, I find it interesting. And also like there is a supplement material about like how they did, like the drag stuff, how they kind of like implement the force onto a still picture. Yeah. So there's a lot of more details. Yeah. I guess that's all for my introduction. Yeah. Thank you. Thank you. Yeah. When I stop sharing here.